Okay. And let's continue. Sorry, let me see who's. Let's continue with Eugenia.
Okay, I am Eugenia. I am from Málaga, but right now I'm living in Barcelona because I come here to study I have studied before electronics industrial engineering, and I have worked on industrialization and hardware validation. And I have come to Barcelona to study my master's degree in electronics engineering. And now I'm trying to focus on digital design and on hardware software co-design.
Thank you. Habits. Haritz, can you introduce yourself? Hello. You cannot switch on your microphone? Okay, no problem. Just write a few words about you. And let's continue with Jordi.
Yes, hello everybody. My name is Jordi. I'm a digital design engineer in OpenChip. I have previously worked in GTD, where we started working with some FPGAs. And yeah, now we switched to OpenChip, where we are working with this RISC-V architecture. So I'm glad to be here and know a bit more about this architecture.
Thank you. Pau?
Good morning. My name is Pau. I am a hardware security engineer and working together in OpenChip with Paul, Jordi, and with Sergi. So yeah, that's about it.
Okay, thank you. Pep?
Hi everyone, I'm Pep. I'm electrical telecommunications engineering student, and right now I'm working in OpenChip in Barcelona in the innovation team on AI optimization. Yeah, so basically that's it.
Okay, thank you. Paul? Paul, hello? I cannot hear Paul.
Hello? Yeah, he's near me, having some mic issues.
Okay.
Well, I can go before him. So, hi, my name is Sergi. I also work at OpenChip here in Gran Via, and I'm with Pau, Jordi, and Paul in digital design, mostly in different security hardware stuff.
Thank you. Sergi Bogatelli?
Yeah, that's me.
That's you, sorry. And there's another Sergi here.
Hi, it's me.
Yeah? Hello, Sergi, yes.
My name is Sergi. I don't work in OpenChip, but I would like to. I'm a computer engineering student specializing in computer architecture and RTL design and hardware-software interface. And I'm also specializing in RISC-V systems, prototyping with FPGAs.
Thank you, Sergi. And finally, Joseph.
Hello, good morning. My name is Yusuf. I studied electronics at UPC Barcelona, and now I'm working at OpenChip as a digital designer. And that's it.
Thank you. And finally, Haritz is a junior HPC engineer at OpenChip also, and currently in his final year studying computer engineering and electronic engineering at UAB, Autónoma de Barcelona, right? I'm based in Barcelona, originally from Aragon. And Paul, he's also working as a digital design for over a year. I have a background in automotive software development. Okay, I think that's it. Nobody else, right? So let's start. Let me see my schedule. Okay, let's review what we asked you to do this week. Last Monday, Christina, were you able to attend the welcome session? Okay, and I think most of you. Hello, we have somebody else here. Welcome. What's your name? Daniel? Okay. Yeah. I've seen you in the registration. Yes. Now that I talk about registration, nobody. There's some people who has not been able to register, I think, yet. I wrote you an email about those problems and who you should contact with. Have you contacted? Have you received any answer? Those of you who haven't been able to register?
From my side, I sent an email, but I got no answer yet. So I guess they are working on it.
Okay.
Yeah, same from my side.
Okay.
Yeah,
Okay, let's wait for them. I'll also write them to see if they answer me. Anyway, well, there shouldn't be any problem with registering in some days. You can start the course and, well, at some time they'll answer and they'll resolve it. At this point, we have 9 people registered. Apparently, it's a problem related with the deadline for registration, I think, because some of you were able to register, but, well, they will resolve it sooner or later.
Yeah. One thing, I just tried registering again, and it seems like it's fixed.
Okay, then you should all try it. Thank you, Joseph. Daniel, were you able to attend last Monday welcome session? Okay, you've seen the slides. You've been able to take a look at what is asked. Okay, so can you introduce yourself?
My name is Daniel. I'm a computer engineering student here at UCM, and I'm on my 3rd year.
Good. Okay. Thank you. Okay, let's go with the tasks that we asked you to do. So we asked you to take a look at module 0, where well, we give an introduction here in this video. I'll take a look now at these slides that are described in the video, in case you were not able to look at it or have any questions. So we'll do that. We'll then take a look at this document, which describes one by one the different tools that we'll use in this course. It starts asking you to install a virtual machine, which is the easiest way to use the course. It's also possible to use it natively in Ubuntu. There are the instructions to install it. You can do whatever you prefer. The virtual machine has almost everything installed, so it's the easiest way. Then you have to download some sources, initial sources with the different tools and the different projects that you'll start working with. And then you have the different tools described, and you are asked to test them. We'll do that also later together to see if you have any problem or any question. So this is module 0. Which is only introduction and installation. You don't need to include it in your final reports. Okay, it's not necessary. Then we asked you to take a look at these slides describing RISC-V architecture, assembly, and instruction format. Probably most of you are already familiar with the architecture, and according to your background, you most know perfectly the RISC-V architecture, so probably you didn't need to look at these slides anyway. They are need, or if you want to review some particular things, well, they are very extensive. They describe almost everything you must know about RISC-V architecture for this course. And then this was the work to be done before today's session. And here we've just published the work to do today. This is module 1. Well, this is the previous work, lessons 2, 3, and 4 about RISC-V architecture. And this is the project that you are going to work in today. It's a complete project about an image processing algorithm. You are provided a project that you first have to test. All the instructions are given here. We'll review them together before you start working on it later. And then it will ask you, after you test that everything goes fine, you will be asked to do some exercises related with the project. Okay, you don't need to finish this today. You just have to progress as much as you can. You can ask us questions if you have questions. If you cannot finish this, you have time after today's session, because remember that you will only have to provide reports, all reports at the end, and the deadline, let me remind you, was 12th of July. The initial deadline is that. If you need some more days, we can negotiate that. It's not a problem. Les paso las placas. We're going to give you 2 FPGA boards. You can keep them until the end of the course, okay? And those are the boards that we're going to use, in addition to the different simulators that are described in the document. Any questions so far, here or online?
Yeah, are you sharing the screen here?
Yes. Sorry, I forgot that. Thank you for reminding me. Sorry. Let's see. Let me know if you can watch my screen now.
Yeah.
Okay. Thank you very much. Well, this is, well, it's not too problematic that I didn't share it yet. Now I'm going to project the slides, the introductory slides that you maybe have already seen. Let's take a quick look at them, and please ask me whatever you need. Here, here, this is what I should use. Well, this is an introduction to the package that we're going to use throughout the course. It's called RISC-V FPGA, or RVFPGA for short. And it's a course that shows these different things: how to target a RISC-V processor called VIR, or earlier SWERF. They changed the name at some time. Now it's called VIR. It's a commercial RISC-V core, and it's implemented in a system on chip that works on an FPGA and on different simulators. It also shows how to program the RISC-V SoC, this RISC-V SoC, how to add more functionality to the RISC-V system on chip, and how to analyze and modify the RISC-V core and memory hierarchy. So it's a quite complete course related with computer architecture, SoC design. The package was developed by Imagination Technologies, that you probably are familiar with this big company. They do GPUs, and they also have developed processors, CPUs, for some time. I'm not sure if they are currently developing CPUs, but they were for some years. And during those years, we contributed to the development of these materials. It was developed by academic partners of the company. We were one, and there are others around the world. After completing the RVFPGA course, in general, users will walk away with a commercial RISC-V processor, system on chip, and ecosystem that they understand and know how to use and modify. This is referred to the complete course. In this micro-credential, we're doing a subset of the course, but it's available for you if you want to extend your knowledge about it. You can interrupt me whenever you want. No problem with that. There are two courses. One is RVFPGA, which is the main one we're working in this micro-credential. But there's a second course, which is also free. You can download it completely. And it's called RVFPGA SoC. It builds a RISC-V SoC from building blocks in Vivado. It installs the Zephyr RTOS. We'll do one final lab about Zephyr in this micro-credential. It runs program on Zephyr, and it, as an example, it runs simple TensorFlow programs. So it's an interesting course that I recommend you to take a look at after you complete this micro-credential. Well, some expected prior knowledge that I think for what you've said, you all have, so no problem with this. This is an interesting book. This is written by Sarah Harris and David Harris, and in fact, they are part of the contributors to the RVFPGA package. And they also have this well-known book that it's available here if you want to get it. It's a good book for reviewing computer architecture in case you need it. The slides that we've provided are based on this book. This one is the book. Well, software and hardware that you need for working with RVFPGA. As for hardware, we say it's optional because everything can be done in simulation. It's recommended to do most in hardware because it's always better, you feel it better. But in case you don't have a board, you can complete everything in simulation. So for those of you who will receive the board and don't have it yet, don't worry, you can still start to work with the simulators. As for software, Vivado is required in case you want to resynthesize the system on chip. We'll use it in some labs in the course. Also, Platform I/O, which is an extension of Visual Studio Code, which is targeted to this course. Well, Catapult SDK was used for some time, but it's now not used, and you're not going to use it in the course. And also Verilator, which is a simulator of very low code, and GTK Wave for being able to see the traces generated by Verilator. Operating systems. In principle, it supports the 3 operating systems, Linux, Mac OS, and Windows. Everything is supported in Linux. Not all is supported in the 2 other operating systems. So the best is to use Linux. And in fact, the best is to use the virtual machine so that you avoid any installation problems. As for the course and SoC, as I said, the course are the main course that we'll use in the course. Although we'll take a look at some others, but the main ones are VIR EH1, especially, and also EL2. EH1 is the big one, EL2 is the small one of the VIR family. And as for the SoC, it's called VIR Wolf, and it's based around this VIR course, and it adds some peripherals to be able to interact with the code. Let me say, I'm not sure if I said, this course, VIR EH1 and the L2 course, were developed originally by Western Digital. They, in fact, used them in some of their products. And after that, some years later, they released them and made them public. And so now they are part of the Chips Alliance group. And you can use them freely by downloading them from the Chips Alliance GitHub. Let's go into the RVFPGA system. Before that, any question? so far? Okay. So the main SOC that we'll use is based on Vir EH1, the EH1 core. Okay. And this picture shows the hierarchy. So we have, in the middle, we have the core. In some places, you will find the old name, which is Swerve. Well, we will refer to it as Vir, but in some figures, it's still they are still using the old name. Anyway, this is the EH1 core in the middle. You have the EH1 core complex, which adds some things such as scratch pads, instruction or data scratch pads, an instruction catch. There's not a data catch, but there's an instruction catch, bus interface, debug unit, some the interrupt controller, some modules are added to the EH1 core. Then we have the system on chip, which again adds some more things to the EH1 core and core complex, such as a boot ROM, the different peripherals, such as the UART, the SPI controller, 7-segment displays controller, GPIO, a timer. So many peripherals are added in the system on chip. And finally, simulating the board. It's a virtual board simulator. Another one is for creating traces to be able to analyze the internal signals in the system. There's another one which lets us see the pipeline, the whole pipeline. So there are different simulators, all of them simulating the same SOC, the Swerwolf or Virwolf SOC. Well, these details about the core and the SOC, I don't think it's necessary to go into them. You probably have already seen the video. You have the information there, and you can see that by yourselves and ask me if you have specific questions. But let's skip this part. Well, this is interesting to remember. You have the memory map in this slide. You will need this memory map later for working with the peripheral. So remember, it's here. You can find it some more places, but here you have it. And this figure represents the different tools or the different tools that you can use. This is the board. This is the virtual board simulator. This is the trace simulator, and this is the pipeline simulator. This figure is old, and the pipeline has evolved, and it has a different interface, but essentially it's the same. It allows us to see the internal signals of the pipeline. And all of them use the same backend, which is the Virwolf SoC. Okay. Well, this is how the SoC is targeted to the Nexus board. It adds several things around it, such as a clock generator. The SoC will work with a frequency of only 50 megahertz. It's a small frequency, but it's enough for our purposes. It adds some more things. It's interesting to see that it adds a DRAM controller, which lets us communicate with the memory available in the board. There's a DRAM memory module available in this board, which we will use in our programs. And also the different peripherals. This board is quite powerful. It includes a lot of peripherals, LEDs, switches, 7-segment displays. It has SPI accelerometer. It has Ethernet. UART. It has many different peripherals. Some of them are supported and some of them are not. And in fact, in the latest years, we have advised several projects where the students were asked to add new peripherals to the board. And in fact, if you see this these connections let you add other peripherals provided by Vigilant, which are not included in the board, but that you can also add and include in your system. So it's quite interesting how I think it's a good work for a final year student to understand all the steps involved in including a new peripheral. And in fact, as we are finally using Zephyr, those kind of works also include working with operating system. So it's quite complete because you see all the different levels. This is the Nexus 7 board, which you already have or will have soon, hopefully. And well, these are different examples of the different simulation tools, which I think we can also skip. In the presentation, after the EH1 system is presented, the EL2-based system is presented. What's EL2? It's the small core of the Vir family. So the Vir family has 3 cores. EH1, which is the main one we'll use in the course, EL2, which is the smallest one, and EH2, which is the biggest core, which we will not use, but it's also free for you to use in case you want from the Chips Alliance webpage. So the EL2 is a smaller core, and we also provide support for it in the RVFPGA package. And in fact, given that it's a smaller core, it allows us to run it in smaller boards, such as these 2 boards that I have here. The Basis 3 board, which maybe you have, you are from this faculty, so you probably know that these are available in the labs. We have many of these here. The reason is that these are cheaper than the Nexus 7 board, but it's quite powerful. And for example, the EL2-based RVFPGA system can be used in this board. It cannot fit in the Nexus 7 board. So these 2 are Vigilant boards, and this one is a quite interesting board, the Boolean board, which also lets us use the EL2-based RVFPGA system, which includes more peripherals than the Basis 3, which includes a more powerful FPGA, and which is quite cheap. This is less than $100. It's around $70 or $80. So it's quite an interesting board. In case you're interested in buying one board for yourselves, I would suggest you to take a look at this one, at least for RVFPGA. It's quite useful. And well, again, I'll skip this part because it describes the EL2 core, the EL2-based SOC, and the different simulators and boards that you can use. So from my side, and for this presentation, I think this is it. As I said, it's described in the video, so you can take a look at the video if you want. And any questions about the presentation? Okay. Okay, let's then switch to the document describing the tools. This is called Práctica Familiarización RVFPGA, and it describes the virtual machine installation, the sources that you have to download, and then one by one, the different tools that we'll use. Have you been able to test them? Have you been able to make them work? No? Okay, you can do that later. You have been able to use all of them, no problems, except for the board, right? That you didn't have it, so you can test it now. Online people, have you been able to test the tools? Any problems? Any comments? Those of you who have any questions? So if you haven't been able to take a look at them yet, you will do that after my presentation. It's the first thing you should do, okay? You should test them and ask us any questions or any problems that you have. If you have already tested them, let me know if you have had any problem with them. You will see that there's a section describing the use of the Nexus-A7 board, which obviously you won't be able to do until you have the board. But the others, you can test them because it's all simulators. Okay. Let me do a quick test with the Nexus-A7 board. I have one here so that you can see how to make it work. So I'll replicate exactly the environment that you will have, although I have the tools installed in my native Ubuntu system. I will use the virtual machine, which is exactly the environment that you will probably use. So I have the virtual machine installed here. The user is called RVFPGA, and the password is also RVFPGA. And it already provides the Visual Studio Code here. So I will open, let me see, because I don't remember the project it asks you to use. So let me go to the document, to the section describing the use of the Nexus-A7 board. Note that all these tools are supported with a video that explains the step-by-step process to make it work. So this can also help you in addition to the text instructions. You will see that there are some installation instructions that you probably have to do before. I have already done them, so I will skip them. So now it asks me to work with this project, okay, RVFPGA BitBo project. Okay, so I will open that project here in the RVFPGA Master UCL-M. The name is because of a master course that we instructed this year and last year. We keep that name to be coherent with the videos and with all the materials. The projects and the BitBo project, I will open it in Visual Studio Code. It's important that the path to the bit stream is correctly written in this configuration file called platformio.ini. And here you should make sure that this path, let me make this a bit bigger. Okay. It's important that this path is correct. Probably it will be correct by default, but you should check. You should check it. Home RVFPGA, the name of the sources, and then SRC, and the name of the bit stream that you're going to download to the FPGA. Also important to make sure that your board is seen by the virtual machine. Okay, here I have it, so that's okay too. And once this all has been checked, I can upload the bit stream into the board. So if you click, well, this can take a bit because it may require some installation and preparation. Now it's ready. So now I come to upload bit stream, this option. I click on it, and the program that I'm going to run gets compiled. Sorry, no. Here only the bit stream gets downloaded into the board, and what I will see is this pattern that is the boot program that is run once the bit stream is downloaded in the FPGA, and it will stay like this: all zeros, this LED on, and this state. Okay. If now I want to run a program, this project provides a program here in SRC called Let Switches CLAN, which you will analyze later. It's one of the programs that you will work with. It's the simplest program that you will work with, and it simply reads the switch state and writes it in the LEDs. So if I have a switch on the bottom, the corresponding LED will switch off. If I change the switch, the corresponding LED will switch on. It's not running yet, so it's not doing that. For running the program, compiling and running the program, I click in this button and then in this button. And with this, the program will get compiled. And it will start running like this. If I click, this lets me debug the program. I can go step by step. I can step into or step over. I can go, I don't think this works. I cannot go back, I think. And I can run until I find a breakpoint or forever, which is what I'm doing. So now I'm running the program. Now the program that is running in the core should read the switches and write their corresponding value in the LEDs. And I can check that it works. If I change, the corresponding LED will change also. Okay? It's the simplest program that you'll use, and it's working on the board. Well, this is just an example of one of the tools that you will use, the main one, the board. But there are also simulators explained in that document that you have to test yourselves. And if you have any problems, ask us. Any question? Okay, no questions. Then let's go with today's task. Let me describe a bit what you have to do, and then you can work on the task after you've tested all the tools. Okay, if you haven't been able to test the tools, please start with that. Install the virtual machine, test all the tools, and so forth. Once you've done that, you start working in the project. So let's take a look at the project. As always, it's provided in the GitHub webpage, and I have it here. Well, the project is an image processing program that by default, it will only read a color image like this and transform it into a grayscale image. That's what the program does. We'll ask you in the exercises to extend the functionality, but for now, this is what it should do. And it's provided in this path. Inside the projects, inside the projects directory, you will find, in addition to these example projects, you will find the image processing project, which is the one that you will use. So you can open that project and look at the programs that it has. The structure, it contains a main function, and which is this function which invokes different functions. The init color image, which only initializes the input image, the color image. The color to gray function, which is the main function here, which transforms the color image to a grayscale image. And then this UART init, which initializes the UART for being able to print things. And finally, the printf nexus, which tells us that the gray image has been created. Well, there's some text here explaining the different algorithms that are used that you should read. So you should read all this theory and understand everything. I won't stop here. That's your job. And it's important to mention that let me open the project here so that we can see it better. No, here, home, RBFPJ master projects, image processing. If you open the project, you'll and you see the sources, you'll see that there are the different files. The main function, which is the one I've just described here, the main function that initializes the image, that transforms it to a grayscale image, and that prints a message, and that finishes. There are some these functions are defined here in the same file, and it's important to note that there's another file called assembly subroutines that provides the RISC-V assembly program for some of the functions. So some of the functions used in the main program are programmed in C, and some of the functions are programmed in RISC-V assembly. Specifically, this one, color to gray pixel. Okay, so it's a project that mixes C and assembly functions. Okay, and that's interesting because in this module we're still reviewing the RISC-V architecture. So this is the best way to review it, with a practical program that uses the RISC-V architecture in assembly and mixes it with a C program that performs the image transformation. You will be asked to first understand how the algorithm works, both in C and this assembly function. So I won't go now in more details because that's part of your job. You will be guided on the process of testing the program. So you should, after reading everything in the document, you should follow these steps to run the program. And note that you can run it both in the board or in simulation. Okay, so those of you who haven't the board yet can do the job in simulator, as explained in the document. You should then follow all these steps, and finally you will be asked to complete some exercises. There are 4 exercises. The first 3 exercises are mandatory. As we said last Monday, some exercises are mandatory, some of them are optional and will be used for increasing your grade, but are not mandatory. So exercise 1, 2, and 3 are mandatory. Exercise 4 is optional. You can do it or not, whatever, depending on your time or your interest, you can choose. But you have to do exercise 1, exercise 2, exercise 3. Exercise 1 is simply to test the project in a different image, which is also provided. Exercise 2 asks you to create a C function that does some functionality. And then exercise 3 is probably the most interesting one, which will ask you to transform functions which are originally programmed in C into assembly, and the other way around, to transform functions which are in assembly into C. And that requires you to understand the RISC-V architecture and the function calling convention perfectly in order to be able to do this exercise. Okay. Finally, exercise 4 asks you to apply a new filter to the image. We are only transforming it from color to grayscale. It will ask you to apply a filter that makes some transformations in the image. Okay. So this is your job for module 1. And these are the 3 exercises, or 4, in case you will also complete the 4th exercise, that you will include in your report. Okay, so your final report for Module 1, you should include the programs for these exercises and also some screenshots, videos, explanations about how you've programmed them, how they work, and so forth. Okay. So from my side, I think this is it. I'll also tell you about the work for the next day, for next Friday, before we finish. But for now, we'll let you work on the tools and on the lab, on the project for maybe an hour or an hour and a half. And then I'll present the job for next session, for before the next session and for the next session. Yes, Sergi, you want to ask something?
Yeah, so just to recap, we need to do from image processing exercises 1, 2, 3 and optionals in this time frame, like today. And then we have some stuff to do before Friday. Oh.
No, it's not necessary to finish those today. It's the work for starting today. If you finish them, that's great. You finish all the work you have to do for Module 1. If you don't finish that, no problem. You continue working next days. And the deadline, as I said, is 12th of July. 12th of July, you will be asked to send the 4 reports for the 4 modules, Module 1, 2, 3, and 4. So that's the deadline. Ideally, this week you will work with the Module 1. You will finish with Module 1 so that next week you can work on Module 2. But it's up to you how you organize your time. And the only thing we require is that you send the reports before 12th of July. Okay. Any more questions? Okay. Well, now you will start working on that. Fernando and myself will be here. We'll be answering your questions, both for you two or you. In case online people has to ask questions, you just switch your microphone on and tell us. We'll hear you. And that's it. Okay. So